Okay, so welcome back. This is number 13. We're at the end of the course. We have 4 more lectures. Let's make the best of it. So, many of you will stop doing macro after this course. And if that's the case, I want you to remember something that you can take, that you can use in the future. Take something with you that you can value. So the point of this last part of the course is to introduce you to the 2 workhorses of macroeconomics, the real business cycle model and the new Keynesian alternative. And they're both, I say workhorses because they involve common techniques and methods that are dynamic and forward-looking and impose a certain rationality on the agents that are taking the decisions, and using that as a sort of a starting point. How do we explain these very common cyclical movements in industrial advanced economies and also in developing economies? Okay. So let's review last time. We'll discuss and characterize the market equilibrium in this model. Remember, this model is a model without money. It's a pure exchange economy where the thing that's being exchanged, the produced good that's being exchanged, can be traded forward in time in a sense, in the sense that it's saved and not consumed. And that's supposed to characterize a lot of things that we do in life, right? A lot of investment decisions, be they in computers or in buildings. Any sort of productive capacity has that notion of deferring consumption today for the purpose of enjoying more consumption tomorrow, right? It's all about that. And the business cycle view of the RBC type is that people are responding to opportunities in the short run because it's opportune to do so. So a boom is a time when people react in a positive way to a positive shock in the production function, a movement of the production function that there's a common agreement because of the price system and because of people's taste that this is a time to work and produce and save for the future. And even though work is unpleasant, we're going to do more of it because we're going to take advantage of this opportunity. And we tend to put most of the weight on technology. This interpretation that Kidlin and Prescott introduced many years ago is that it's a movement of the production function that we would like to attribute it to some movement in the way economies convert capital and labor into output. And it's persistent, but it's not permanent. Part of it may be permanent and foreseeable, but to a large extent, these things fluctuate and we react to them. And characterizing that equilibrium requires us the use of a few equations, right? We're trying to formalize, get a bit more advanced than just drawing pictures. The next state we're going to do is we're going to try to identify what happens when the economy sort of stops moving. So it's a little bit like growth theory, first half of the course, except we're in discrete time, right? T equals 1, T equals 2, T equals 3. And we'll try to identify what the economy's steady state would look like. And it doesn't have any shocks. It's completely still. It's like the pond in the morning on a peaceful summer morning, right? Nothing's happening, and then someone throws a rock out there and the waves start. It's kind of the way you want to think about this. Now, to understand how those waves work, how the economy reacts to these small changes, we have to approximate the economy with a linear alternative. And that's a big step that's common to this approach and to the one we'll do in next week and the weeks after. And there are 2 technical ways to solve this that you'll learn in this course. One is using matrices. Okay, it's a little fancy, but it's very efficient, at least in our view. And the other one is to use substitution and undetermined coefficients. So this is like, I think the solution looks like this, and if it were the solution, if I plugged it in, what happens? And indeed, it looks like the solution. So it's kind of like guess and verify. It's very intuitive. So there are 2 ways to do this that you would want to learn to apply to the RBC model and to the new Keynesian model in the future. These are somewhat technical aspects, but you're master students, and I know you can do this because all the students before you, all the generations on whose shoulders you're standing have done it too, okay? Then we want to be critical and say, why is this not the end of the road? Why is this not satisfactory for our purposes? Well, one reason must be because it doesn't have money. It doesn't have a financial sector. So this exercise proves, in some sense, that having a financial sector is a good idea. And because money is supposed to be neutral in the long run, maybe something else that needs to be assumed as well. It's not just enough to have money. You need to have money plus some inability of the economy to fully reflect the neutrality that we kind of know money has to have in the long run, but in the short run can't. Okay, so that's the magic of macro. That's what kind of the legacy of Keynes. We'll talk about it in detail next week. Okay, so last time it was technical. I introduced this for those of you who were here. If you weren't, watch the video. We introduced the ingredients of the first of two workhorse models, the stochastic growth model or the RBC model, real business cycle. Real because it's real, no money. Okay? It looks a lot like the growth models of the previous half of the course. So the intuition you'll get from that is carrying through. There's no disjunction here. There's no disconnect. Okay, but it's a different way of looking at time. Time is no longer continuous, it's discrete. And that's because in macro, in short run, business cycle macro, we only have quarterly data at the best, maybe monthly data, but we don't have GDP data at the monthly frequency. I can't monitor GDP every second. I can only monitor GDP this quarter, last quarter, the quarter before. I can take an average, it's not, and we know GDP is like a flow. It's like water running under the bridge. So in principle, if we had lots of money and lots of computers, we could probably monitor GDP every second. So when you go to bed at night, what happens to GDP? It goes down because you're not working, you're not producing. The factories probably aren't running their third shift. And if they are, you'll still see it in the data. But we don't want to do, who cares about that? We're not going to monitor GDP every second, every instant. Okay, if you're a meteorologist, you care about monitoring the temperature every second. It's probably very, very interesting. For macro, because it costs so much. We don't want to be observed like that. I don't want people to know when I go to bed and not working. Okay, so we tend to focus on the quarterly sampling frequency. Just a fun fact. Yes?
Is there a chance that we can turn off the AC because it's really hard to...
I don't know what it is. I don't think it's the AC. I think it's something else. I think it's the fan on the on those beamer, those projectors. So I can't touch that. We could test it. If I turn it off, then maybe it'll not come back on again and sabotage the entire lecture. So we're not going to do that. All right. So last time we looked at the household's decentralized problems. The idea is having a representative household. The representative household faces prices today, but also prices in the future. This is a smart household that maximizes expected utility, and it knows that it can't predict exactly what the wages and rental rates of capital are going to be in the future, but it can make a pretty good forecast. I'm going to assume that it uses this model to forecast it in some sense. So it's got an internal consistency, remember? So this sequence of market prices is you planning your household behavior, your labor supply, and your savings behavior for the next period, i.e. what you don't spend out of your income to produce, to acquire more capital in the future. And because there's only one good in this model, and its only differentiating feature is the time period, then if you don't consume today, you've automatically accumulated some productive capital for tomorrow. Right? So it's like that models, like this class of models we did last half of the course. Now the firm is also facing the same market prices. So in equilibrium, the price that the firm has to hire labor at is the wage that the household is supplying labor at. So the equilibrium would be the common wage that equates supply and demand in each period, and the common rental rate of capital, this gross rental rate we call U, is that same price that would equate demand and supply for capital. Remember, capital is, in a period T, is given, so it's all about demand and an inelastic supply. To get supply of capital to rise, you have to save today, and tomorrow there'll be more capital around. So that's one of the inherent reasons we have a business cycle, is we react in a very strong way to shocks, and we start building houses, and these houses are built, and then after a while, maybe the reason they were profitable is no longer there. Think about all the investment in the IT sector that's being called back now, right? And if you read the newspaper, you'll see that. That's another example of investment. Well, maybe it's no longer as profitable as we thought it was, and we've got this equipment hanging around. What are we going to do with it? Okay, so you end up having this accumulation. The driver in this model is total factor productivity, right? The position of the production function. You can call it technology. A lot of the fans of the RBC approach call it technology, but it could also just be regulatory change. It could be the change in the terms of trade. The price of your country's exports might go down if you think of it as a small open economy. We're just going to call it technology. Okay, that's the standard in this field. And then we characterize this decentralized market equilibrium. I'll write it down again for you. Here are the ingredients. Remember, the nice thing about this is the intellectual purity of this model. It's so easy to discuss it with your friends and neighbors because it's just very simple. There's very little room. You can't really argue about ideology here. This is just a setup. We've got production function. We've got preferences of agents. We've got capital accumulation. And we've got this technology, which is moving through time. It's getting shocked, and it has persistence. What's the persistence in the model? What's causing the persistence in this technology? Getting some feedback from you today. You understand that the magic of this approach is that you've really got all the assumptions on the table. There's no room for discussion here. What is making technology persistent, i.e. not white noise? Yeah. Anybody else want to try?
It's based on the last period.
Yeah, but what's the parameterization of that dependence? What's the parameter that's going to give us that persistence or not? Think of it as a dial. You can turn it up or down. What parameter? What Greek letter? Yeah, rho. Rho. So rho, if you make rho close to 1, the technology is really sluggish in the sense that if it gets shocked, it's going to stay like that for a while. It's going to take a long time for it to come back. Okay, this is an AR1 process, so it's really very restrictive. But if rho is close to 0, then the shock is here today, it's gone tomorrow. That's going to be an important driver in this model. So the persistence of the technology shock will actually be inherited by output, GDP, et cetera, in the equilibrium. That was one of the critical points of this setup that people criticize. It's kind of, it's an issue that made people move towards other approaches. Okay, so keep that in mind, rho. Rho is important. Now, we set up the optimization last time. That was kind of difficult. We had this Lagrange function. That's something you have to learn how to do. And the first order conditions say, if I'm at the optimum, small changes in the Lagrangian resulting from changes in my control variables won't increase the Lagrangian. So I've reached an optimum. And those first order conditions have great interpretations. The first one, the marginal utility of consumption in every period is equal to the marginal utility of relaxing the resource constraint. This is probably something worth writing down because in an exam, I might ask you to actually interpret the first order conditions. You understand? So if you're doing the best you can, it can't be the case that I can increase my consumption and make myself happier because there's a cost to it. If I consume more today, I have less savings tomorrow, less capital tomorrow, less production tomorrow. And if I'm doing the right thing, I should be indifferent between that and not doing that. I should not do it, period. I shouldn't change consumption anymore because I've already chosen it optimally. The second first order condition says, my labor supply as a household will balance the gain from work, which is more resources, more consumption, with the cost. What is the cost of working more? Yeah, you lose the leisure. And if you lose the leisure, you're less happy. So there's got to be some optimality there. That's the second first order condition. It's an intratemporal condition, just like the first one. Okay? So if you work to the point where it's getting increasingly painful, and the value of what I'm getting for it doesn't really compensate anymore. And what I get for it is wage times the marginal utility of more resources today. Right? So you combine those first two first-order conditions, you actually get something. You can eliminate lambda, and you end up getting the marginal utility of the marginal rate of substitution of consumption for leisure is equal to the real wage. And that's something you've probably seen in microeconomics in other courses. Somebody turned off the fan. Did you do that? The third condition is an intertemporal condition. This is the Euler equation. This is the same Euler equation we did last half of the semester. Remember? How do I tune my consumption over time to make it slope the right way? Right? Is consumption relative to tomorrow more or less attractive? And if it's more attractive, then I'll choose to consume more today. And if it's relative to tomorrow, and if it's less attractive, I'll consume less relative to tomorrow. I'll be saving relative to tomorrow. Okay, so it's a relative thing. That's called the Euler equation. This equation says that the expected rate of some measure of the expected rate of growth of marginal utility is going to be very close to what I'm getting from resources today. So if I could get a little bit of extra resources today, it would be worth the value of saving that resource for tomorrow. And how do I save it? I have to defer consumption and have more capital tomorrow. Capital tomorrow has a rate of return that's ut plus 1. And then I have to count on depreciation minus delta. And that's going to be what I get for that in terms of goods tomorrow. What's the value of the goods tomorrow? It's going to be lambda t plus 1. So that balancing of current versus future consumption in expected value terms is an incredibly important part of macro. It basically says when the rate of return is high, I'm going to save in expectation, but it's an expected value. So it's an expected value of a random variable times a random variable. So it's not going to be trivial to solve. Right? It's not, because we know it's not equal to the product of the expected values. It's a more complicated expression. And the first derivative with respect to the Lagrange multiplier implies that the budget constraint for the household holds. And here I've substituted in equilibrium the fact that income is equal to the sum of labor income plus capital income, which exhausts GDP. There's nothing left over in this economy. The last one is just simply no monkey business in terms of saving for no evident reason, okay? Because remember, this Euler equation balances consumption today versus consumption tomorrow. You can see it by substituting the first order condition in there, but it doesn't tell you the level of consumption. That's true for a whole bunch of paths, consumption today relative to consumption tomorrow, but we want to do the best we can without gaming the system in some sense. We can't game the system because we have these resource constraints that limit our ability to produce, but we can also maybe save too much. And that would be ruled out by this last condition, the so-called transversality condition. Just make sure that we don't save excessive amounts for the rest of time. Build pyramids. Pyramids had some productive function back in the days of ancient Egypt. I'm not sure what they were, but they built a lot of them, and a lot of people worked really hard to build them. I hope it was worth it. I mean, it's worth it for tourists like you that go to Egypt and look at them, but I'm not sure it was actually as productive as people thought it was, but that's a different question. Okay, so we can substitute and make this a little bit simpler with the model. Okay, so I've cooked this model down a little bit. Look, I've got 4 equations now, and it's a dynamic system. KT is a state variable today, so I can't change it. I can only change KT plus 1. So it's really 4 equations in CT, LT, ZT, and KT plus 1. And ZT is exogenous. I can't, it's like technology. Well, today we've got a new innovation that helps us write exams and problem sets, you know, Chat GPT 3.0. That's a technological innovation. It's a big one. And I'm sure a lot of you are going to try to use it when you write your master's thesis. We don't know what to do, right? It's increasing your productivity in some sense. It's increasing the productivity of the whole economy. It's got all sorts of other side effects. That's the kind of technology they're thinking about in this. But that's exogenous. You can't influence it in this model. It's coming from above. But it's driving the system. It's the only source of fluctuations in this model. Okay, so the next step is to find what is the steady state. We did this before in the old days in continuous time, right? What happens when the water is still? The waves have stopped. Okay, what happens? Well, z is constant. If you turn off the shock, there's no more shock to z. And when if z stops changing, and it won't in the steady state, it will, but the steady state is a fictitious type of construct. It's what would happen if the economy were really still, not moving anymore. How could we characterize it? Okay? And that's what it would look like. Okay, everything's growing at G in this economy that has some unbounded feature like consumption, capital, and the technological process, because there's a driving rate of growth there. L is not growing, right? Because you only have one unit of time per day or per quarter that you can use, so it's bounded. So L is bounded. We can't work we can't work more and more and more. The amount of time we need for that is limited. So that's a different object. So its steady state of L is going to be a constant value of L. The other things are going to be growing. So how do we do that? Well, we can write down these equations that track everything that grows at rate G, and wages, the real wage also grows at rate G in this model. Because it's Harrod neutral technical progress. It's making labor more and more productive. Capital doesn't automatically get more productive in this model, right? And we can write this set of restrictions to give us what's called a balanced growth path. And a lot of really smart people have looked at data for many years, and even now, where we think the wage share is falling, it's actually starting to rise again. Since the pandemic, it's started to rise. There's no presumption that the wage share is shrinking. I'm pretty strong on that. I have a paper on that. People discuss it, and we don't know what the future holds. But in terms of the long run, if you look at the Netherlands, for example, the Netherlands has really good data. So if you go back to the 1920s, the labor share in the Netherlands, including what the government takes from labor and redistributes through the pension system, through the unemployment benefit system, through the health system, is fairly constant. It's remarkably constant. And the same is true of the United States. Okay, you have some swings, but the U.S. labor share has gone down, but if you go back to the 1970s and 60s, it was rising. So the notion is this restriction on our model is going to be constancy of labor share, which is actually delivered by the Cobb-Douglas function in competitive wage and capital rentals. You had a question.
Do we take that the user cost of capital is constant also?
Yes. Yes, it is. Actually, I mean, there's a lot of discussion of that too, because of, the crazy thing is that like real interest rate has been falling over the past 15 years, 20 years in real terms. The question is that the user cost of capital? There's a whole set of issues. What is the user cost of capital? The price of capital has been falling, so that means if you buy a unit of capital, on average, you might be making a capital loss. So, we have to do this properly. And if you go back another 50 years, interest rates were higher. So again, this is a restriction that the model imposes, okay, but we can discuss it. But I mean, this model, if it doesn't go to labor, it has to go to capital and vice versa. There's no other beneficiary. There's no like third party. There are just two factors of production, two ways you can pay out the GDP, okay? So that's a really key assumption. That's going to help us. Watch what this helps us do. It helps us restrict the model because under these conditions, we can look at the ratio of y over k. In this model, it's constant. And it's pretty stable, we know that from the beginning of the course. It's also pretty stable in Germany and the United States. Even though real wages have been growing, GDP is growing, y over k is relatively stable. So we're going to use that. Okay, capital productivity is one way of looking at it, y over k, or k over y, the capital coefficient. Therefore, C over K is also fairly stable. Consumption is a flow, capital is a stock. That ratio is also fairly stable in modern developed economies. If you're developing, you're still kind of moving in that direction, but it's a fair point. And the wage share, I already mentioned that. Okay, so let's see what that buys us. I'm going to say the beginning of time is 0. I'm going to call it, I'm just going to drop the 0. So z in period 0 is just z, and y in period 0 is y. And I can plug in those values in the first order conditions, and I end up getting the following. A lot cancels out. All the exponential growth goes away. And you can see what I get. I get sort of a long-run marginal utility of consumption at the very beginning, or the average period over time, if you like, related to the marginal utility of consumption tomorrow, and my impatience, beta, and the growth rate of the economy. And you can massage that a little bit and get the following expression. And that restricts G, beta, delta. What is delta? Depreciation rate. And of course, y over k. And that's a relatively stable object. So in some sense, we've put a restriction. If you take the model seriously, it puts a restriction on the data we can observe. So those things better be pretty stable. Okay, and we can't arbitrarily choose delta without thinking about what it's going to mean for G and beta. Okay, so it's like tying down your hands. You can't choose any parameter you want. You have to choose the ones that make sense with the data. The second one says the marginal utility of leisure is related to the what? To the wage. And the wage can be written as a function of the wage share relative to consumption to give us this marginal utility equivalent, because 1 over C is the marginal utility of consumption. So the marginal utility of leisure is going to be related to the marginal utility of consumption times the long-run real wage. Okay, and the final one is the resource restriction, which just says that the capital tomorrow has to be allocated between what's left over the capital of yesterday or today plus output minus consumption. So we've got this restriction coming from the model. Now that's just the steady state. We care about the cycle. We want to understand how the cycle is moving around this steady state. So the next step is to approximate this hairy model in a linear form. Log-linearization it's called. And this is a great, if you go into finance, for example, or other fields, this is a really useful technique to have under your belt. Okay, it's basically a way of approximating this complicated model and getting a solution to an approximated version of that model. So let me just state the strategy first. Steady state growth path, use the grand ratios as a guide, as a restriction, and then maybe if I have some external information, which I do, I'm going to impose that to get the parameter values, because I can't just make up delta. I have to have some information on what is delta. Delta is depreciation. Is it 5% per year? Is it 8% per year? That matters a lot. You know, it matters a lot. Then we're going to log linearize. I'm going to show you how to do that in a second. And then we're going to look at the dynamic behavior of this linear approximation to the model. So that's the standard methodology we'll use from now going on in. We're not going to look at that horrible set of nonlinear equations because that's really hard to solve. We're going to approximate that thing because for small changes, a log linearization is really, really close. It's a good approximation. If we can do that, then we can use the linear approach, which is what we did 2 weeks ago, and Leopold has shown. Poor Leopold, he's still in bed, but he's okay. He's getting better. Good news. okay? So that's our trick. We're going to do that. And again, we're still in the spirit of Slutsky, because when we take this linear economy, this log-linearized economy, it's going to get shocked, and we can simulate it. We can plug it in the computer. The computer can help us produce some pictures. We can look at the response to a single shock. That's called an impulse response. And we can also study the stability of this system. Is it stable? And does it look anything like Germany, Netherlands, USA, Britain, okay? Or China? And there are people working on this. People are still, I mean, I know one of my PhD students is in China right now, and he was working on versions of the RBC model as a way of trying to account for some interesting characteristics of the Chinese economy. Remember, we have a state variable we can't change. We have a control variable for this household. This representative household is choosing consumption and consumption tomorrow, and thereby choosing investment and choosing labor supply in response to these shocks. And tomorrow's state variable will be a function of her decisions today and those shocks. Okay, so I can really, once I linearize this model, I can really cook it down to a very simple set of equations. You could put it in, plug it into a spreadsheet or use MATLAB and just, you could play with it yourself. Okay, that's why this is a valuable technique. Let me give you an example of what log linearization means. This is where you have to learn how to do something. This is like learning how to use a screwdriver or using a hammer. You know, you don't use a screwdriver to put a nail in, you have to use a hammer. So log linearization is a way of making everything look log linear. If you can't do that, then you can't do the next step. So let's take this example. This is a linear relationship between capital tomorrow and capital today, and output today and what I consume today, right? That's not log linear, it's linear. So how do I massage it to make it log? I have another problem is the thing is growing over time and we want to look at deviations, so that's going to help us. Remember, we have a trend and we have deviations from the trend. So we can make that first equation sing for us by rewriting it in terms of the last equation, in terms of K bar and K hat. K hat is the percentage deviation of K from K bar. Okay, so this is just an identity, what I've got here. I've just written as an identity, and then I'm going to approximate it with this. I'm going to basically write the whole system in terms of these hats. Y hat, K hat, C hat. So all I've done is I've taken that first equation and I've used the definition of E and log and this hat to rewrite this very simple looking equation. But now you see what I've done. I've got basically a part that looks like a function of the logarithm of something relative to its trend, and then I've got the trend. So I've already separated the trend from the stuff I'm interested in, which is the deviation from the trend. Okay? So this hat notation is key. Once you start seeing the hat in macro, it means we're talking about deviations from the long run. And that's what macro, for most people, is a lot of people like the growth part, but most people like the cycle, right? The cycle is the hat. So you can think of that as either the logarithm of the ratio of xt to x bar. X bar is x is any variable you like that's growing, okay? You can also think about it as the fractional deviation. Approximately the log of the ratio is equal to 1 plus the fractional deviation. Remember, these two are kind of equivalent, and that's why we're using a log linear approximation. If I can write it in that form, then I can make everything look like deviations of the logarithm of the variable from its long run or trend value. Okay? So again, if you learned anything as a master, you'll learn that the ln of 1 plus x is equal to x approximately. Approximately. That's really a useful object. I mean, when you go off, like I said, if you do finance or you just look at things that are growing, you know, trying to get a quick a quick manipulation and write down a growth rate, this is the way to do it, right? So we can write basically this object like this. Okay, so KT is equal to its trend value times 1 plus this approximate logarithmic deviation from its steady state. Okay, so once I do that, I can plug in these trend values, these trending values on all the positions of that last equation, and I can write the thing like this. Okay? And then basically in the steady state, I know this is true. So I can basically subtract the last equation from the second to last equation, and I get that. Okay, so this, if I can eliminate k, and I've got this linearization of the previous expression, which is true as deviations from the steady state. There's no more trend in there. It's all about the deviation. Look at it very carefully. You don't see any bar value in there anymore. The only thing you see are these grand ratios, y over k and c over k. Those are constants. Those are constants. So this is a linear equation in these hatted values, k hat, y hat, and c hat. So I've taken what was a linear relationship and I've rewritten it as a log linear approximation. Now, why is that interesting? Well, k hat has the interpretation of a percentage deviation, right? A percentage deviation, not an absolute deviation. And that's independent of the size. Compare Luxembourg, Germany, United States, China. It doesn't matter. It's about percentage deviation. And that's why these coefficients have the interpretation often as elasticities. They relate percentage changes to percentage changes. Now, I've magically turned this one equation into a linear equation in the logs. Previously, it was in the levels. We can do this with all the other equations. And Leopold will take you through some practice steps. It's really quite easy. Once you learn how to do it, it's like riding a bicycle. Once you've learned how to do this, then you can do a lot of interesting stuff. So we can take that thing, this set of four equations and four unknowns, and we can log linearize it to look like this. It suddenly looks like something we can play with, because all these coefficients are constants. And they're all these multipliers times these interesting variables we're trying to study are constants. Okay, and if it's a linear system with constants, we can solve for the endogenous variables and get an answer. So we have four equations now in C hat, KT hat, or KT plus 1, depending on how you want to look at it, because KT plus 1 is endogenous, LT hat, and ZT hat. Okay, so this is the magic transformation. Once I do this, I can go to town. I can actually try to solve this. I can try to find out how the system responds to one shock. That was the impulse response. Or I can shock it every period and see how the cycle plays out. Is it a long cycle? Is it a short cycle? On average, it's not going to be a perfect, we learned that 2 weeks ago, it's not going to be a perfect sinusoidal curve. It's going to be something that looks like the business cycle that we have. It's the Slutsky idea, right? Okay, so reality check would be the calibration part. I already told you about the grand ratios. Do they make sense? What grand ratios can I use? Okay, I know if I'm studying Germany, I'm studying quarterly data. K over Y is probably a number like 9, or maybe 10, maybe 11, depending on how you measure the capital stock. C over Y, who wants to take a guess? What's C over Y? $40? A little bit low, but he's on the right track. It's between 0 and 1. C over Y has to be less than 1. You can't consume more than you earned, right? Because GDP says you, and this is a representative agent that has no access to foreign lenders. So it's going to have to be between 0 and 1. Anybody want? I mean, 40% is out there. Anyone want to do better? Do you think it's higher? Probably higher. 80. Okay, that's a bit high. This is fun, you know. Economics can be fun. Well, there's kind of a magic number that you should always remember. It's about 2/3. It's really about 2/3. In Germany, it's lower. In America, it's probably a little bit higher. Some people say it's more like 0.6. The problem is, I'll tell you what the problem is, how do you count the government? The government is also consuming. And in the United States, the government doesn't consume as much. Why is that? Because the United States doesn't provide as much public health care as the Netherlands or as Germany does. Therefore, government consumption in America gets counted as private consumption. This university is paid for by the German government. In America, it's paid for by private households. So that consumption gets lumped into American private consumption. So you can't just say, oh, let's just compare C over Y. Oh, it's high in America. The Americans are wasteful people. No, you have to know exactly what's going into C and what's going into G. So a lot of people say, well, let's just take G and C and put them together. That's probably a better approximation. But again, some countries like to spend more on public goods in general, so it's not going to be perfect. But anyway, for the private household, you have to be careful. It's a little reality check. So calibration is really important. We need to get the linear coefficients, we need to look and scratch at the data. We have to find out what's going on in the data. Okay? It's always a function of the deep parameters in this model. This is what's called first principles in macroeconomics. We are forced to make everything related to these parameters, otherwise we're cheating. We can't cheat. Okay, so we're forced to figure out what alpha is. We're forced to figure out what beta is. You know, these are all things that we have economic interpretation for. What is eta? Eta is related to the Frisch elasticity of labor supply. So 1 over eta is my response to a temporary change in the real wage in terms of my willingness to work. Okay? So the higher that thing is, the more output is good. Output and labor supply is going to move to an increase in the wage that a real business cycle model would bring forth. So we need to, this is what Prescott said. I mean, Prescott, the late father of this model, he just died just a few months ago. They should have to do with, if you take the model seriously at all, it has to somehow relate to what we observe. Otherwise, just throw it away and do something else. Study physics. Right? And this is one reason the RBC model is kind of, it's on the shelf and we use it a lot, but it's not the standard because it fails in a lot of ways. It doesn't match everything, but we can match the capital share. In this model, that's clearly alpha. We can match the growth rate. We can measure that just looking at the data. Even though it's changing sometimes slowly over the long run, maybe we can take an average over 40 or 50 years and start with that. And we can get C over Y and K over Y from the GDP accounts. This is called discipline by data. The data force us. Otherwise, don't do it. Okay? And that's, again, Joan Robinson, don't be snowed by economists. This is the point. You know, use the data. Okay, so we've already done this. Now we're going to do it. How do we do it? Well, if you look carefully, you saw that there was a KT plus 1. So when you choose your consumption as a household, you're choosing KT plus 1 at the same time. Because what you don't eat, you got to be putting into the machines for production tomorrow. Okay? That has to be the case. That's called the resource constraint of the economy. So we build a lot of buildings now. We're going to have buildings tomorrow that we have to somehow deal with. I mean, I walked by this building over there this morning, and I noticed that those office buildings are empty. Isn't that weird? I think they kind of overdid it. This building was built like 15 years ago. You know, we can discuss whether it was a good investment for the investors. Maybe they got a big tax break or something, but we got this building there. What can you do? Why aren't they renting it out right now? Their expectations of the rent they were going to get were too high, obviously. They should probably convert them into apartments and let people move in there. That would be probably the socially optimal thing to do. I don't want to comment on that, but it's just a fact. There are a lot of empty buildings around this neighborhood, a lot of empty storefronts. So, you know, if you save a lot today, you're going to have a lot of capital tomorrow. And that, you could say that was bad policy. In this model, it's always the right policy. You just thought you'd have more use for it in the next period. And you have to find out the path of the economy that's consistent with the decisions you make. And that's what the solution of this model is going to mean. We have to solve this set of deterministic linear difference equations. And then later we'll let it hit by these shocks because we know how it's going to react to a single shock. Control variable we defined, the state variable we defined, and we know, I just told you, the capital stock tomorrow is a function of my control decision today. I can't change today's capital stock. I can't build another one of those buildings or build one less. It's already there. I'm stuck with it. You know, in China, there's a big discussion right now. It's very interesting. They think they may have built too many apartments. So there are a lot of people in China that, you know, went into debt to buy apartments, which is a great investment in general. You know, it's one of the ways you can become a capitalist. You can rent to yourself. But you better do it at the right time. If you buy when the price is too high, you're going to sit on a capital loss. And the bank that lent money to you to do that is also going to be kind of upset. Okay, so all these things happen, and you can relate it to this representative agent model in some abstract way. But in this model, it's only about the Z. It's only about the fluctuations in Z that make this economy sing. We're going to try to do that now. We can eliminate L. L is easy because L depends on contemporaneous variables. So it's like I could get rid of L. We had 4 variables, now I'll make it 3. 3 little endians. Okay, get rid of L. Solve for L in terms of Z hat, K hat, and C hat. I already got rid of Y hat because Y hat is a function of Z hat, L hat, and K hat. Capital, labor, and the shock. Okay, so and again, this is just in the interest of simplification. We know how to do log linearization. I've just shown you, but there are lots of little subtle tricks you can use. It all involves writing this variable in terms of a deviation from its trend. That's all about that. If you can do that, you're golden. You can do it. Okay, so how are we going to do this? In this course, we're going to consider 2 methods. One is called the matrix eigenvalue decomposition. So I'm going to try to write this as a vector-valued equation. I'm going to write those 3 variables, K hat, C hat, and Z hat, as a moving vector through time. This is why learning matrix algebra in high school or in college was useful. There are some times you can really use it. This is the only way to do this. Well, this is the only way to do this without using a lot of math, a lot of algebra, which is the second approach, guess and verify. Method of undetermined coefficients, MUC. If you want to remember that the way to remember things, and B.F. Skinner taught us, is you just have to make up crazy mnemonic devices and repeat them many times. So MUC, method of undetermined coefficients. But the first one is the more elegant, beautiful one that actually is used by macroeconomists today. But if you want to, you can always have recourse to the method of undetermined coefficients, which just means you have to guess that the solution looks a certain way, and then you check to see that it does, and then you find out what those undetermined coefficients are. Guess and verify, right? It works because we're in a linear world. It's right. The linear solution is the right solution. Everything else is kind of dodgy. You have to be careful, okay? So write that down. It's useful stuff. Let's try the first one. Method of undetermined coefficients comes afterwards because I'm going to use the method of undetermined coefficients to verify that this one gives us the right answer. They both give us the same answer. Okay? And to remind you, the solution means writing the control variable as a function of the state variable. And that means consumption as a function of the current capital stock and the shock. That's my objective. If I can do that, then I've got a solution because I can shock it 1%, I can shock Z by 1%, I can tell exactly what consumption is going to do, what capital stock tomorrow is going to do, and I can let that system run out on MATLAB or a spreadsheet. Okay? So we've already log-linearized the model. Now I'm going to write it in a fancy way using a moving vector. Vector moving through time. Okay, it's going to look like that. But the reason I have that E in there is because it's the expected value of t plus 1 values of K, Z, and C. It's just for completeness. It's going to look like this. Once you plug in the shock, you're going to have a vector of kt plus 1, zt plus 1, and ct plus 1, depending on, and again, everything with a hat. K hat t, z hat t, and c hat t. And A is a matrix, a 3 by 3 matrix of coefficients that we just found, we just solved for. Okay? This looks like a beautiful machine, right? It's got this deterministic part, and then you've got this random part. The random part is the driver. If I turn that off, then I have the steady state, basically. If I leave it on, then every period I get a shock, and it's only one shock. It appears twice. It's going to appear once directly in the determination of technology tomorrow, and it's going to determine my consumption behavior tomorrow as well. And we're going to have to solve for that coefficient, but we'll do that later. The point is, I've got what's called the state space representation of this model. You can call it that in this course. If you do the PhD, there's a bit more subtlety involved, but this is it's like a machine, right? We had this beautiful model, we log-linearized it, we put it in this form, and now this A is going to be a 3 by 3 that just has all that information in it, all those coefficients that I had in the previous slides. Yeah? Why is it 3 by 3? Well, 3 by 3 times a 3 by 1 is going to give me a 3 by 1. Right? There are only 3 endogenous variables. Yeah?
What are all those constants?
I just told you, those are all functions of the underlying deep parameters. So, go back. After we get rid of L hat, they'll all be functions of alpha, beta, K over Y, K over C, or C over K. Those are the deep, and those are constant. They don't change. Okay? So, I mean, they're nasty. Now we have computer programs that do all this hard work for us. I mean, if you go on to do research in macro, there's a wonderful program called Dynar. It's written in MATLAB. There are even more fancy versions that are written in Python that actually do this for you. But again, I think it's important for you to know how it's done before you put it in the Küchenmaschine. You have to know what you're making. You have to know the recipe. Okay, that's the idea. So let's stare at that a few more minutes. It's based on the log linearization we just computed. Okay, so the next question is how do I find out how this system behaves in the sense of what is this undetermined coefficient there, and what are these undetermined coefficients that link consumption to capital and Z. So this is a fancy way of trying to argue what we learned in the first half of the course is absolutely relevant for the second half of the course. And this is called the eigenvalue-eigenvector decomposition, because it's going to basically ask, what happens if I take this system, okay, we have 3 components of this vector, and what would happen, can I somehow simplify the solution by rotating this vector and then unrotating it? I'm going to solve it using the rotation, and then I'm going to go back and unrotate that vector. That's why it's called eigenvalue-eigenvector decomposition, because we're going to use the eigenvectors of this A matrix to turn this vector kzc in a certain direction in a way that makes it easily solved, and then I'm going to rotate it back. And I can do that because it's a linear system. Okay, so what does that mean exactly? It means I'm going to take A, and I'm going to write it like this. It's going to be the product of three matrices. One is the vector of the matrix of eigenvectors, so omega, 3 by 3 matrix. This is also a 3 by 3 matrix, and the inverse of omega is a 3 by 3 matrix. Lambda is a diagonal matrix, and along that diagonal are the eigenvalues of A. And that's a really magical property. You can't do that with any matrix. You can do it with matrices that have certain properties, and this model has those properties, so I'm going to be able to do this. This lambda is a diagonal matrix, so there's zeros off the diagonal, and along the diagonal are the eigenvalues of A. And that's kind of important, because those eigenvalues are going to tell me whether the system is stable, unstable, or saddle stable. Okay, so starting back, taking this decomposition. Now remember, if I take a vector and I hit it with a matrix, what am I doing? I'm moving it around. I'm sort of moving it like this or like this. In three-dimensional space, my arm is a vector. Okay, so I hit it with a matrix. I turn it, and if I do this, I turn it this way, or I can make it go backwards. If I hit it with a certain matrix, it doesn't change direction. It just gets compressed or stretched. Okay? That's the definition. That's the definition of the eigenvalue. Okay? I'm basically multiplying it by a matrix that gives me a compression or an extension. And that extension is simply what lambda is. Okay? And the vector for which that compression or extension applies is called the eigenvector. So if my arm is an eigenvector of A, if I hit it with A, I'll basically get this, or that in the same direction. So the transformation of pre-multiplying that original vector with omega inverse means I've rotated the matrix to look like this. So using the tilde, the Germans would say Schlange, this symbol, I've basically transformed this system into a system that is only dependent on its previous values. Remember, lambda is a diagonal matrix. What does a diagonal matrix look like? Just remind us. Lambda 1, lambda 2, lambda 3, 0, 0, 0, 0, 0, 0. So whatever I hit that with, it's going to be basically it's going to be expanding or contracting these values by this constant. It's decoupled, so K tilde does not depend on Z tilde or C tilde. It only depends on its own past. And that's special because that means that if I know what the future, if I take 10 periods in the future, the value of K tilde is going to be only a function of K tilde in period T raised to the power of T, the eigenvalue raised to the power of T. Okay. It's a rotation that allows us to solve very quickly because we know that we can see very quickly that what's going to matter, powers of these eigenvalues will tell us whether this system is stable, globally stable, or unstable. Because if one of these lambdas is greater than 1, that means that whatever the value of the tilde value in period t, if you take t plus cap t periods in the future, that thing could be growing very fast. If the eigenvalue is greater than 1, that thing is going to explode. So the eigenvalue test for this model would be, for a globally stable model, all of these eigenvalues have to be less than 1 in absolute value. That's called the eigenvalue test for absolute stability. So, is this interesting? Absolutely, because it's going to tell us whether the system is nonsense or not. If the system globally explodes, then it's not going to be very useful for us. So the underlying values of the model, parameters of the model, will feed into the eigenvalues of this A matrix. So for global stability, we're going to require that all the eigenvalues of A are inside the unit circle. So remember the ASAD model? You can write that in the same form. You can write the ASAD model, if you wanted to, in the same form that we had before with this A matrix. And the eigenvalues of the A matrix of this ASAD model have to be inside the unit circle for stability. That's true of any dynamical system. But in this model is special because one of the variables is forward-looking. So that means that it's possible that consumption, because it's a forward-looking variable, causes the system to have one eigenvalue that's outside the unit circle. And if that's the case, powers of something that are outside the circle, unit circle, it cannot be positive at any time. So that means that this transformed variable that is a linear combination of C, K, and Z has to be equal to 0, because 0 raised to the tth power does not explode. Okay, so the requirement that this model have some form of stability, it smells and looks like the same kind of saddle stability that we had in the Ramsey model. Okay, there's exactly one value of consumption that can possibly bring us back to the steady state after being shocked from the steady state path. Okay, remember, consumption is a control variable. The household controls consumption. And in this reduced form, you've got C, K, and Z. There's only one value of consumption that responds in a way that is consistent with stability in this model. And that's called the saddle stable solution. Okay, and how do I find that saddle stable solution? Well, I just told you that this eigenvalue property, if that eigenvalue, and I'm going to call it 3, if it's greater than 1, then if I'm raising something that's greater than 1 to a power that's a positive integer, that thing is going to get bigger and bigger over time. That cannot be stable unless C tilde is equal to 0 in every period. Okay, so that means that a linear combination of my original variables has to be equal to 0. And that's going to guarantee me saddle stability. And if you think about it, if that's the case, then CT has to be a function of KT and ZT. And there's a unique function. So there's a unique combination of CT, of ZT and KT that make the sum of those three equal to 0. Otherwise, the model would imply explosive behavior. We don't observe explosive behavior. So we need to impose on the solution that C tilde is equal to 0 for all periods. So consumption is, people are forward-looking, they have a shock, they know what they're doing, they're optimizing, and along this approximated path, the solution imposes that C hat T is a linear combination of K hat T and Z hat T. Okay, so that's how we're going to find this solution. Okay, so again, I rotate the system so that all the elements are orthogonal to each other in some sense. That's called the eigenvector, eigenvalue decomposition. Then I impose stability, and then I rotate it back. And that's how I find CT. So CT is a linear combination of KT and ZT. And in T plus 1, it's going to be a linear combination of KT plus 1 and ZT plus 1. So the shock and the current capital stock, which can't be changed, are going to determine my consumption in every period. That's the solution to the RBC model. And why do we know that these are linear? Well, omega is the matrix of eigenvectors. Omega inverse is a matrix of constants. And we can choose the third and the third row in the first column element, and its ratio to the third, and the third is exactly the linear combination that sets this object equal to 0. Okay, that sounds really complicated, doesn't it? I mean, but in some sense, it is the only solution that is consistent with rational expectations and the model's discipline of imposing optimal behavior on the choice of variables in this model. This is a saddle stable solution, so there's only one value of CT that works. Remember in the Ramsey model, if you were off that magical path, you didn't make it. To reach the intersection in the Ramsey model, you had to get the right value of consumption. And in fact, if you look closely, you remember it was a function of the capital stock. So it's the same kind of analysis, except now we have a shock. In Ramsey, there was no shock. You were just solving for the optimal growth of the economy. Okay, so it looks like Ramsey, but it's more involved, and it's got randomness. It looks like it could explain, maybe possibly explain the business cycle. This notion of where the eigenvalues are is what's called the Blanchard-Kahn condition. So if you go on to do macroeconomics for a thesis with Professor Weinke or myself, you look at the model's eigenvalues and in the log-linearized form, and you have to look and see whether not too many of the eigenvalues are outside the unit circle, because if that is the case, the thing will explode unconditionally. There is no stable solution. Okay, so the rule is you got to have as many roots out or eigenvalues outside the unit circle as you have control variables, jumping variables, co-state variables, if you like. Okay? That's called the Blanchard-Kahn condition. Now that sounds extremely complicated. There's an easier way to do this, which is called undetermined coefficients. It'll give you the same answer. It'll give us the same solution. It'll give current consumption as a linear combination of the capital stock and the technological shock in the current period. Okay? And the easy way to do it is just say, I'm going to assume the solution looks like that. What do I get? Okay? So I've kind of shown you using matrix algebra that there's a solution there, and it's unique. The solution method number 2 is basically undetermined coefficients. I'm going to say consumption depends on K and Z, or C hat, because we're in a log linear world, C hat will depend on K hat and Z hat in a linear way. Okay, and then I'm going to say, now that I know that, I'm going to plug it in and see what happens. And then I'm going to solve for those coefficients. So it's kind of like cheating, actually, but it works. Okay, so I'm going to say, I know this. If you think about it, we already know the answer. We solved for it using method number 1. But I'm going to say, well, since I know how that matrix looks, and I know that CT is going to depend on these other two things, I'm going to call them eta, elasticities, not the eta from the model. This is elasticities. So it's unfortunate use of notation, but the subscripts say eta is the elasticity of C with respect to K, and eta CZ is the elasticity of C with respect to Z. Remember, because we're in the log linearized world, that's exactly what these things are. They're elasticities. Economists love elasticities because percentage change, it doesn't matter how big or small you are, right? You should remember that. So I'm going to guess that this is the answer. I guessed it. Guess, and I'm going to verify that it's the answer. Okay? If that's the answer, I can plug it into my first order conditions in the log linearized version and then just solve for the implied values of the the role that K and Z play for C, and match them with the original assumption, which is up there. And then I just solve for eta. Eta CK and eta CZ. So Campbell showed this in a nice paper about 30 years ago that you can do this, okay? And in a sense, we still use this. You can do the same thing using linear algebra, guess and verify for a whole matrix of coefficients. The solution is identical, okay? The solution is the same, so that's good news. I'm not going to show you what the solution is. It's kind of nasty, but it's a function of all those variables that we already solved for. So once you've done that, you're kind of, the rest is fun. The rest is, I shock the model, what happens? What is the dynamic response over time in response to a single shock? And this is a nice example of that. It's called an impulse response, okay? So this is an example of that model we just looked at. This is from work of a colleague of mine who used to be at this university a while back. He's now in Chicago. This is a single positive shock to technology in the RBC model. It's a beautiful picture. It's in color. That's why I stole it from him. It's a great picture. Okay? So what have we learned? The agent, the household, responds optimally to this shift of the production function in the positive direction. So what happens? First off, the capital stock is given. So for a given capital stock, the production function is more productive. If labor hasn't changed, you're going to get more output for sure. Right? Just by accounting, you're going to get more output. Not surprisingly, output goes up in response to this single shock. Again, this is one shock, and then you take away the shock after period one. It disappears. Now, the wage goes up because the marginal product of labor goes up. The marginal product of labor contains total factor productivity. I mean, the production function is more productive, so the productivity of capital and labor have gone up. So people see a real wage rising because firms are willing to pay more to hire labor. Labor is more valuable, and workers will respond to this temporary shock in a positive way. The substitution effect dominates. The Frisch elasticity is positive. Okay? So people go, and this is an example of where the Frisch elasticity is really, really big because the Frisch elasticity is 1 over eta. So this is like, really, really short-term increase in wages. People really want to work and take advantage of it. So labor rises. Now, the labor can't go to infinity because you only have 1 hour, 1 unit of time every period. So eventually leisure becomes valuable to you, and you're not going to work like a. You cannot work more than 24 hours. So labor goes up. Now, if labor goes up, productivity is up. You're going to have a lot more output. You're going to have more output because of the direct effect, and you're going to have more output because of the extremely interesting opportunity for labor to work. So the household's working hard, and the household is consuming more. Consumption goes up because the household has more resources, but the household doesn't want to eat it all today. The household wants to build up the capital stock for tomorrow. So the capital stock is rising very slowly, but it's rising. So even in response to a one-off, very productive shock, the household kind of puts a lot of those resources into the future. And it enables that household to consume more, not just today, but tomorrow, next day, next day, next day. The household is smoothing consumption, like we observe it in Germany, China, United States, okay? So you can see consumption jumps because that's the surprise, and then the household tries to smooth consumption, just like it does in the real world. What else do you see? Interest rates, they don't rise very much. They rise a little bit, but you can't see it. It's that little greenish curve there, okay? That's interest rates, because interest rates don't need to move a lot to make things happen, okay? And technology, of course, is the exogenous shock. That is not to be explained. That is the explanatory factor. So that's the classic response to a positive shock to technology. We get a boom, okay? And you can think about putting this on its head. What would happen if we had a negative shock? So, use your head a little bit. What could cause the production function to move in for a country or for an economy? One thing could be the price of energy goes up, right? The productivity of capital and labor, holding everything else constant, has gone down because natural gas is 500% more expensive. That causes a recession in this economy, less investment, capital decumulation. Literally, people invest less than they would, so the capital stock could even shrink for a while because you're investing less, you're eating what you should have been investing, but you're still smoothing your consumption. So this model is attractive because I understand how it works. I'm not making up anything. This is the way it works, and if it doesn't work like that, then the computer made a mistake. I made a mistake. I programmed it wrong. But we can really make a one-to-one assumptions in results. That's why the RBC model was so popular in the 1980s and 90s, because it generated a lot of excitement, and a lot of that excitement is carried forward to the other type of model I'll discuss next week, which is the Keynesian approach. Because now we think we should really take people seriously, the way they decide to consume today and tomorrow, the way they invest, and the rest. Yeah?
Why the labor goes down to 0 after 5 years?
Good question. Okay, it's a great question, but we can't answer it because I think I understand this model. Now, if you accumulate a lot of capital, that makes you wealthy. Right? And if you're wealthy for a long time, how do wealthy people behave? They take it easy. Take it easy, man. Take it easy after a while. It's called the wealth effect. And eventually the wealth effect dominates, like your parents. I haven't gotten there yet, but at some point when you sort of finish your life cycle, you want to take it easy, play a little golf, right? That's exactly what's happening in this model. And because of that initial shock, the economy is wealthier for a long time. And these are deviations from the steady state trend, which is growing. People can be accumulating capital anyway, but this is the response years, according to this calibration, to a one-period shock. It's pretty interesting, right? It's just one way of thinking about the way economies deal with this type of change.
What about technology? Why does it decrease?
Yeah, because it's an exogenous shock. Remember,
Is it coming back?
it comes back because it's rigged to look like that. That's what we assumed. That's why rho is less than 1.
So they had just like one period, they had a better technology that
And then it's basically, the rest is just the past into the present. Okay, that's an assumption. Remember, we didn't prove that, and we didn't even. It's not even first principles microeconomic behavior. Now, a lot of people criticize this model because of that reason. Okay, so that's exactly you're getting to the critique, which is, I've kind of put a lot of interesting economics here, but I still don't know what's causing this technological shock. Well, I'm sorry, I can't tell you. The next iPhone, I don't know even what it's going to look like. We might be wearing, virtual reality glasses and whatever. Some things don't work, like the iWatch didn't work. No one uses that anymore. I know one person who uses that. Apple Pay works. That's a good one. There's lots of technology. It's not just that kind of technology. It could be hydrogen, green hydrogen. The next efficiency gain, and that could have a huge effect on our lives, right? These are all the things you want to translate into. Or maybe we learn how to use plastic to make building materials. We can build houses for everybody. Everybody can have his own mansion made of plastic from the ocean. Okay, so I want to finish up. The strengths of this model are obvious, right? It's really attractive because we can think about it, we can discuss it, but it's also pretty realistic about certain aspects. So one of the things that attracted me when I first started looking at this is that everything goes in the right direction. C and I and Y all go up in a boom and they go down in a recession. That's not always true for the alternative. The variability of investment is the highest because it's responding immediately to the shock. Consumption is smooth because we know people like to smooth consumption. That's the model is hard-baked. It's hardwired to give that prediction. Okay? Interest rates are pro-cyclical. pretty decent implication, which is a little bit tricky with the new Keynesian model, because aggressive reduction of interest rates actually stimulates the economy. It kind of goes against what we see in the data. The Burns-Mitchell diagrams don't give us that. The eyeball evidence. Remember I told you about Burns and Mitchell? They're coming back. Okay, there's some econometrics as well, but let's look at the Burns-Mitchell. Okay, there's real GDP. There's a recession. Looks like a surprise. This is the average behavior over 40 different countries. No, sorry, 40 years of 8 countries, lots of cycles. Recession is kind of an abrupt thing. It's kind of a surprise. It's a shock. You got to deal with that. Consumption doesn't move as much. It's a little bit less volatile. Investment is very volatile. So we nailed that one. The RBC model does pretty well with that. Okay? Government purchases, kind of flat. Government's not doing much. Or whatever it's doing, it averaged out to nothing. Maybe sometimes it puts the accelerator on, sometimes it puts the brakes on, but the average behavior is pretty boring, probably because it's all civil servant wages that doesn't move much, right? Consumption, government consumption is a lot of that is government salaries for government employees. Labor productivity is pro-cyclical. In recessions, it goes down, so we have to deal with that. That's a hard one for the new Keynesian model to beat, okay? It's easy for the RBC model because that's the reason everything's going up is we're more productive. Interest rates are pro-cyclical. And government spending causes interest rates to rise. So this is a little subtle point for those of you who like this stuff. When governments get into wars, they have to spend a lot of money and resources on guns. And where do they get that money from? Well, you and I don't want to pull in our belts. Let the future generations pay for it. Okay, and if you put that type of extra consumption in the economy, you end up getting interest rates rising with government spending. So Robert Burda has shown this in a very long, look how old this data is, going back to the 1700s. Whenever the UK government got into a war, real interest rates went up. It's not in the model, but if I put it in the model, it would give that implication. If I just come in, like if we start a war, a big one, someone's got to pay for it. You know, this is awful. That's why war is really bad, because it just eats up tons of resources. And a lot of governments say, well, I can't force our households to do it, so we're going to stretch it out. We're going to borrow from our future generations. And that generally makes interest rates go up. Another way of saying that is the current generation has to buy the debt, so to make them buy the debt, you raise interest rates. So it's kind of a little subtle point. What are the weaknesses of this model? Obviously, we'd be done with the course if this was enough. This is just one way, one lens of looking at the data. The weaknesses are myriad. There are lots of weaknesses of this model. I think the guy in the back already pointed it out. Maybe he wasn't even thinking about it, but he elucidated a critique of the model. Okay, although these variables are correlated, the wage share is supposed to be constant in this model, and it ain't constant. So the model is not getting it right here. Even though it's stable in the long run, it's fluctuating. And it seems to be counter-cyclical. So in booms, the wage share goes down, the labor share goes down, and in recessions, it goes up. So in some sense, the wage is not keeping up with productivity for whatever reason. So we need to do better. The persistence of output is still too low, and it comes from the gentleman in the back who asked about rho, the persistence. We've cooked it. We assumed rho to be close to 1 so we could make the model look like the business cycle. That's not very satisfactory. I mean, you want to explain something. So the biggest criticism of the RBC model is that technology is cooked to be persistent. It's not really endogenously persistent. So that's a good that's a Joan Robinson criticism. You know, she's don't let economists fool you. And capital is persistent too. Like if I build these buildings, they're going to be around next period. It gives us some persistence, but it's not enough. It's not going to give us the kind of persistence we see in the data. You can add government spending, like I said, but again, using the war example, some people might like that example. When you have a war, people feel poor. And they understand the government's taking my resources and throwing it into the garbage can. I mean, imagine how many buildings are being destroyed every day in Ukraine. How much work and capital went into building those buildings in the past 30 years. They're all getting wiped out. Over the past 100, think of World War II, how much capital in this city was destroyed. You see it just by looking at these modern buildings. There used to be other buildings there. So what a waste that is. So people feel poor, and then they compensate by working harder because they feel poor. Some people like that. I think it's a bit far-fetched, but maybe some people think like that. Okay? Because if you have less wealth, you increase labor supply. He asked the same question. You have more wealth, you reduce labor supply, right? And old Burns-Mitchell helps us here too. So these are great pictures. Look, I love this. Look at labor productivity, pro-cyclical. Employment, pro-cyclical. Real wage is fairly smooth. It's also kind of a puzzle. This model doesn't predict that unless the elasticity of labor supply, the friction elasticity is extremely high. I don't think it is, but that's just me. The real wage share, or the wage share, that's the wage divided by productivity, is counter-cyclical. So it goes down in booms and goes up in the recession. It's another way of thinking that the wage doesn't respond quickly to productivity. No money. Okay, there's no money in this model. And the original attraction was, wow, maybe we don't need credit and money, maybe it's just a veil. Karl Marx said that. Karl Marx said that all this money stuff is just a sideshow. The real stuff is C plus I plus G. So Marx didn't think that way, but he was right. I mean, in this sense, there is a role for a model that has no money, but it's not probably the right model. Okay? And the last one is the one that hurts me the most, is in this model, if you're unemployed, it's your fault. It's because you're lazy. You don't want to work. Or because you're responding to the lower real wage. Okay, so again, economics is always an approximation. So this is the biggest weakness, I think, and the biggest criticism of the RBC model is its view that unemployment is a purely voluntary phenomenon. It's withheld labor supply. Okay, so in booms, people are working hard because, well, it's opportune to do so, and then in recessions, we kind of take a little protracted vacation. Not so realistic. Realism isn't a criterion, but maybe it's not getting close to what we think is going on. Money seems to matter. This is the Burns-Mitchell for money. Look at that. So about 4 quarters before the recession starts, the real money supply, and we know what that is. We learned it from the Sadrowski model. M over P starts to stagnate. And there are many ways of explaining that. Prices are rising faster than money, or bank credit is restricted, or the demand for money is going down, but something's happening there. That's a really robust fact. If you want to predict the next recession, keep your eye on the money. Okay, so this is a good one. Take a look at that stuff. Next time, we'll do the Keynesian alternative. I want to just finally make these last few remarks. We know how to do this now. We can do this with other types of approaches. We don't have to do it with the RBC model. This is called the stochastic, the dynamic stochastic general equilibrium approach, DSGE. Okay, it's been criticized, it's been praised. It's our bread and butter. State the model clearly, state your assumptions. What are the first order conditions? Characterize the equilibrium, find the steady state. Log-linearize around the steady state. Play with the log-linearization as an approximation. Parameterize using the data. And then look at how the economy responds. Okay. Thanks for your patience, and next week it'll get even better. See ya.